So you probably saw some of these if you've gotten into your review much. Saw ones that are like this. And what's probably the best first step for anything with only words? Yeah, you should draw. So preparing to take off implies that this thing is on the ground. And it says the angle of elevation. What does that mean? So looking up from what?
The ground. Eye level.
Yeah, from the horizontal specifically, right? Like in terms of where to put your angle. But you're right, in this case, it doesn't say. So, I mean, reasonable conclusion would be that you're looking from standing up, right? But this doesn't say how high you are. I do want you to think through it though as if you were, or as if it was given. So let's say you're 5 feet, or your eyes are at least. What are we going to do with the 5 feet at the end?
Subtract it. Add it.
Add, yeah. So let's work this problem with that 5 feet, and you'll see your answer pop up here, what I'm labeling H. But we'll add our 5 feet to get the total height of the thing. Okay? Alright, so angle of elevation is 28 degrees. It goes there with the horizontal, and it says that we're 50 meters from the balloon. What kind of problem is this? Okay, nice. You just went right to it. So trig ratios, of course we can assume that's a right triangle. And remember SOHCAHTOA? Yeah, so she said tangent, which is opposite over adjacent. Remember, opposite is across the triangle from the angle that you're working with. Like directly across. And then adjacent means what? Just in general, what does adjacent mean?
Like right next to.
Next to, and then H, of course, is hypotenuse. Opposite over adjacent. I'm just going to, I'll put some letters, I guess, on here. That would make more sense. So, tangent of 28 equals H, little h, over 50. How do we solve for H in that case?
Get it by itself. So multiply 50 by both sides.
Yeah. Okay. What do you have to check before you just start punching buttons on your calculator? Yeah, since it was given in degrees, make sure that it didn't switch over to radians. It doesn't just do that on its own, but if you happen to reset it, change the batteries, or borrow one of mine, then definitely check that it's in radians. Let's start over. 50. I said radians, I should have said degrees. Check that it's in degrees. 50, tangent of 28. It's 26.6. What's the label? Meters. And then total. So did everybody get 26.8? Sorry, 26.6. That's the way the problem was written. Any issues with that? Okay, so I just added this 5 to make it more realistic, because I don't think anybody's probably going to get down on the ground, right? Crouch down with your phone down there. So, let's talk about something we haven't done in quite a while. How would you solve for x in that triangle? In fact, why don't you find a spot and write this down? It's an easy enough example to write down. Does anybody raise your hand if you know how to solve it? Okay. Bailey does. You? Okay. Well, Kyron, talk me through what you're thinking right now.
I was thinking maybe we could like see if we can use like law of sine and law of cosine because we know it's not a right triangle.
Okay.
What's given, so we can't use like trig ratios and stuff like that. So use other theorems like all that.
Yeah, so remember the SOHCAHTOA is only for right triangles. That's really important because back on this test, between your class and the other geometry class, a fair few people would do law of sine, or sine or cosine when it wasn't a right triangle. So make sure you check that condition first. So he said it's not a right triangle, so probably law of sines or law of cosines. Let's review those. First, this one. Remember we had a side lengths A, B, and C across from angles A, B, and C. And so what was the law of sines? Do you remember? You will need to use law of sines on your test. So that's why we're reviewing.
Isn't it like sine like big A, for example, under like just little a equals, and then the same but like sine B, little b, sine C, little c.
Yeah. Good. And he said the sine of B or C over little c. I don't want to write it because remember we only used 2 at a time. Okay? But basically it said the sine of an angle over its opposite side is proportional throughout any triangle. So remember you can use law of sines on any triangle you want. It doesn't have to be right. It doesn't have to be non-right. It can work on both. And some of you ended up liking law of sines more than trig ratios actually. Do you remember that? Okay? And you're welcome to do that. You can, if the situation allows, you can use law of sines if you want, and not trig ratios. Okay? Let's do law of cosines too. And I'm just going to leave the same picture up there because we can use the same letters. What was it? Are you raising your hand? Your finger? Yeah, good. Like this one, right? So if you have side, angle, side. That's a law of cosines scenario. What's the other one? Do you remember? Okay, that's okay. If you have all sides, remember you can use law of cosines with all side lengths known. Can you solve for side lengths if you know all the angles? Like what if I give you a triangle that was just like 20 degrees, 80 degrees, of course I'm not drawing these to scale, and 80 degrees? Can I use law of cosines or law of sines to get x, let's say? I have a yes and a no. Anybody want to break the tie? Well, let me ask you something. If I told you to draw a 20, 80, 80 triangle, are we all going to draw the exact same one? Because this could be one, but you might draw on your paper one like this size, and then someone else out in the field draws one like that size. So can we just make up a length? No. So if I just give you angles, you can't solve for lengths. That's part of that whole triangle congruence concept. Okay? Anyway, law of cosines. Anybody find it? Go.
A squared equals b squared plus c squared minus 2bc times cosine a.
Awesome. Yeah, and we always put these in parentheses when we actually plug numbers in. So remember, you only solve. You either solve for the first side length, which is opposite of this angle, but you don't solve for B and C with this. That's not why we use it. And so let me say this. Must be opposite of A. Okay, so you have to set this up in a way that the side length by itself is across from the angle that we use in the formula. Okay, that's the only condition. So in here, what are we're obviously going to use law of cosine, so what are we going to set up? Actually, now that you know that, why don't you give it a shot? I don't want to take that opportunity from you. So in this one, we're solving for a side length, which means that where the A is will be our variable. What is B? Yeah, either 10 or 13. Cosine of what? And then this whole right side, is just some number, right? You can actually plug that whole thing into your calculator if you want to. How do we get x by itself? Square root, yeah, so let me go get that whole number and then we'll square root it. So 72.8. And then we can square root that. So 8.5. How'd that go for you? Awesome. How about solving for the angle? What's different about it? You guys remember? If I go back to just this equation, what was different about solving for big A, the angle? Well, you can't directly just plug it in. That's true. Good job.
Would you use the inverse?
Inverse cosine to undo the cosine. Yep, good job. And then there was a big caution, maybe two, but it's kind of the same thing. Remember what that was? Yeah, remember you had to subtract these two over, not the 2BC. And remember, it was always super tempting because it would say something like, I don't know, let's say 900 equals 500 minus 400 cosine of A. And it's like so tempting to subtract that and get some easy small number. Remember that? But remember you had to subtract off the 500 in this case and then divide the negative 400 off. So be careful with order operations was the caution. Alright, let's do a law of sines problem. Maybe I shouldn't have said that and just let you pick. This is going to be one that this is called an ambiguous case. Maybe I shouldn't do it that way. Let's just do the usual. Cannot do it. Okay, go on with that. Okay. Solving for theta. Why do I say my labels are kind of dumb? Yeah, the shortest length is on the longest picture. Let's just make it 20. So remember, we take sine of the angle over its opposite sides, which is 15. and then sine of some known angle over its opposite side. So over 10. And then how do we solve these kind? Butterfly, yeah. So it'll say 10 sine theta equals 15 sine 27. Now we want to get theta by itself. How? By what? Huh? By what though? You are right, it's divide. So we're working to get here to this theta by itself. So what can be divided? There's actually only one thing. Yeah, it's just this 10. Because remember, theta and sine are hooked together through a function, not just multiplication. Okay, now what? How do we undo sine? Yeah, that's the inverse function. So sine inverse of sine, that cancels that whole thing out. There we go. So those two are gone, and we're just left with theta, and then we have sine inverse or inverse sine of this whole thing. Okay, and then remember, you have to have some care with your parentheses when you plug that in. When you do inverse sine, it automatically opens parentheses, so that's the whole parentheses. Then we have 15 and another sine with parentheses, sine of 27. That's where we have to make sure to close the 27, the angle, parentheses for that sine, and then divide by 10 and close the overall, and now you're good. So let's call that 43 degrees. How'd that go?
Yeah, I just didn't realize we were doing half. I used 12
You did?
Yeah, I got the same thing.
Good. She said she used law of cosines, which is okay. Definitely there's some overlap in methods sometimes. Let's see, and so, yeah, because we have all three sides, so you can absolutely use law of cosines just fine. Okay? Alright, last thing maybe for today to review, we'll see. Let's say I have some triangle, and, come on, it's working. There we go. 50 degrees, 65 degrees, and I don't know where it's double. 60 degrees and 70 degrees. Let's do that. So remember there are relationships between sine and cosine. Starting over. I don't want law of sines and law of cosines, but ratios. So what do I have to have? 90. Good. Let's make this 35 and 55. Can everybody see those numbers? Okay, so in terms of these, remember if I said sine of 35, what is the ratio for the sine of the 35 degree angle?
B over C. C.
Good, B over C. So what of the remaining trig ratios, sine, cosine, tangent, of either 35 or the 55, what is equivalent to B over C in terms of ratio? In other words, I want to be able to fill in a different left side but have the same right side. Does that make sense?
Cosine of 55.
Ah, so she's saying this. Do you guys agree? Cosine, remember, is adjacent over hypotenuse. So she picked the other angle and said, well, B is adjacent and C is still the hypotenuse. What's true about these two numbers, just the 35 and 55? They are angles and they add up to what? 90, okay? So we call those complementary. So the sine of one angle is the same as the cosine of the other angle. So we could do a different version of this. If I said sine of 55, what letters is sine of 55? A, so opposite over hypotenuse. So A over C. So what would have to go here to be equivalent? Cosine of 35 is A over C. So notice how if you change the angle to the other acute angle, then you change sine to cosine or cosine to sine, whichever way you're going. Okay? So let's say it again. Sine of one angle is the same as the cosine of the other angle, the other acute angle. How does trig stuff feel? I feel like we reviewed the hardest parts, which is law of sines and law of cosines. Feel okay with the rest of it for now? Okay? So far we've kind of talked through review about the trig, similarity, and some polygon stuff. So how do you feel like your review paper is going so far, like work on Wednesday? Is it going okay? Any of those? Well, how far is everybody? How far did you end up?
The second page.
Alright, page 2.
I'm like scattered.
Oh, you jumped around. Okay.
I have a few papers to do.
Okay. Well, are there any questions on that you would like to ask about that have stumped you? No, just show me.
That one.
Alright, so she's talking about this is page 2, right side. Asking about EF. So this one. Anybody remember how to do that one? Well, what do you notice about the markings? Oh, that says what? Not almost, but
It's bisected.
yeah, the angle is bisected. Those angles are congruent, right? So even though it's angle notation, it's actually telling us that this is called the angle bisector theorem. This is on your yellow note. See if you can find it. It would be right at the end of the note part. Well, yellow. What color was similarity? Maybe I shouldn't say yellow.
That one, no. It was blue.
Blue. It's on your blue note. Sorry about that. Angle bisector theorem.
This is the mountain.
Yeah, this is the mountain one. Good job. It's just upside down. So that was what we talked about, how to recognize this scenario is the mountain. Snow on the mountains, yep. So what was true about snow on the mountains, angle bisector triangles?
If an angle or triangle is bisected, it divides the sides proportionally.
Yeah, so remember so this angle is bisected, so it's saying that these two pieces can be written as a proportion. So tell me, Silvana, what that would look like. Okay. Yeah, you got it. Okay. So that was kind of a small topic that we stuck at the end of similarity a while ago. So I can understand why that was in the archives. Any others that you need to ask about before we work for a bit? Number 9. How are we counting that? Is there actually a 9 on it? Oh, what page is it on? Which one? Oh. This one?
It's
Okay.
about
I figured out that one.
Each exterior. So this goes back to polygons, which was orange. So what is true about exterior angles of a polygon? Yeah. So they add up to 360. And remember, it was just we just wrote total equals 360, I believe. Right? Is that what it says on your formulas? Yeah. Okay. Alright, so this one is talking about each exterior. So we switched over, or not switched, but we edited this formula with what? You should have it in there. Over n, yeah. Do you have that? Okay. Okay, so now we just plug in what we know. So it says, what is it, 20? 20 equals 360 over n. How do you solve for n?
Plug in.
Get it by itself, yep.
Like 360 by both sides.
Well, it already is, though.
It's divided.
It's like 360 is in the numerator, so it's multiplying.
So divide it.
And I would rather work on the n myself, because that's the one we care about. Does that make sense? Like n is trapped down in the denominator,
Okay.
so let's get it out of there so it's in the right spot.
We're just gonna say multiply n by both sides.
Yeah. So then we get 20n. 20n equals 360. Now what? Yeah. What is that, 18, I think? Not degrees, but 18. Alright, any others? Alright, so you have just under 30 minutes. Please, please, please ask questions.